8 minutes ago, on top of a mountain in Chile, a telescope the size of a small building took a picture that no instrument in the history of astronomy has ever been capable of taking. And before I tell you exactly what is buried inside that image, stay with me until the very end of this video, because the last part of this story is the part almost nobody online is talking about yet. And once you hear it, you will never look at a single point of light in the night sky the same way again. Let's start with the basics, because you need to understand exactly what this machine is before you understand why the entire astronomy world has been losing its mind over it. This is the Vera C Rubin Observatory. It sits on top of a mountain called Cerro Pachon, high in the Chilean Andes, roughly 8,800 feet above sea level, in one of the driest, darkest places on the entire planet. Astronomers chose this exact spot on purpose. No clouds drifting through the field of view, no city lights bleeding into the horizon, almost no moisture in the air to blur the stars. It is, quite literally, one of the best possible locations on Earth to point a camera at deep space. Here's where it gets interesting. This is not just another telescope perched on a hill. Its primary mirror measures 8.4 meters across, nearly as wide as a tennis court is long. Bolted to that mirror is a camera, and calling it a camera almost undersells what it actually is. This is the largest digital camera ever. Constructed by human beings, built with a resolution of 3,200 megapixels, or 3.2 gigapixels. For comparison, the camera in your phone probably captures somewhere between 12 and 50 megapixels per photo. This single instrument captures roughly 100 times that in a single exposure. Every image this telescope takes is so massive that if you wanted to display just one of them at full resolution, you would need several hundred ultra-high-definition television screens lined up side by side just to show the whole thing at once. And here's the part that really demonstrates what this machine is capable of. It does not creep along slowly, capturing one careful photograph every so often, the way most observatories work. It moves fast. Right now, on any clear night, it is capturing a brand new, richly detailed image of the sky roughly every 40 seconds, then swinging to the next patch of sky and doing it again, all night long, taking around 1,000 exposures a night for 10 years straight without stopping. Why 10 years? Because the actual mission behind this observatory, the one 2 decades of construction and planning have been building toward, is called the Legacy Survey of Space and Time, LSST for short. The plan itself is almost hard to picture. Instead of one snapshot of the universe, Rubin Observatory is scanning the entire southern night sky in ultraviolet, visible and near-infrared light, revisiting the same regions roughly every 3 days, continuously for an entire decade. String those repeated images together and you are no longer looking at a picture of the universe, you're watching a movie, an honest, uncut movie of the night sky changing in real time, built from actual observations rather than simulation or animation. The scientists running the project have called it the greatest cosmic movie ever made. On June 30th, 2026, that movie officially started rolling. But before we get to what has happened since then, it's worth rewinding, because this observatory carries a very human story in its name that most coverage skips entirely. It is named after Vera Rubin, an American astronomer who, decades ago, was studying the way galaxies rotate and noticed something that should not have been possible. Based purely on the visible matter inside a galaxy, the stars, the gas, the dust we can actually see, the outer edges should spin noticeably slower than the regions closer to the center, the same way planets far from the sun move slower than planets close to it. That is not what Rubin found. The outer stars in the galaxies she studied were spinning almost as fast as the inner ones, which meant something invisible had to be out there, adding extra gravity, holding those galaxies together from the outside in. Her patient, careful measurements became some of the strongest evidence scientists had for the existence of what we now call dark matter, a substance that emits no detectable light, yet appears to make up a significant share of the mass in the universe. When the National Science Foundation and the Department of Energy built the most ambitious survey telescope in history, naming it after her was not sentimental decoration. It was a continuation of exactly the work she started. The engineering behind the camera itself deserves its own explanation because building it was its own decade-long story. The instrument, roughly the size of a small car and weighing close to 3,000 kilograms, was constructed by the Department of Energy's SLAC National Accelerator Laboratory, working with teams spread across the globe. It carries 6 large optical filters, each tuned to a different band of light from ultraviolet through to near-infrared, letting scientists study everything from hot young stars to faint, distant galaxies within a single coordinated survey. Every image has to pass through layers of calibration, focus checks, exposure checks, alignment checks, before it becomes part of the official dataset. Because a mistake baked in at this stage could ripple through 10 years of observations with no way to correct it later. That is part of why the commissioning phase took as long as it did. The team behind the project has said publicly that the decision to officially begin the survey only came after a careful operational review covering image quality, survey speed, system uptime, reliability, and calibration accuracy. Because once the 10-year clock starts, there's no going back to quietly fix small errors. None of that raw data simply sits on a hard drive in Chile. It travels to a data facility in the United States, hosted at SLAC, where it becomes available to a wider scientific community, including a group called the Dark Energy Science Collaboration, researchers around the world using Rubin's observations to measure the fundamental properties of the universe with unprecedented precision. And unlike a lot of major astronomical projects, this data will not stay locked behind institutional walls. Scientists have said this is the first time this much astronomical data will be available to this many people at once, opening the door for researchers everywhere, not just at major institutions, to participate in real, cutting-edge discovery. Eventually, even members of the public will be able to explore parts of the dataset themselves. It helps to understand just how much this single project cost and how long it took to get here, because the numbers put everything else in perspective. Rubin Observatory is a joint program funded by the National Science Foundation and the Department of Energy, with a total cost of roughly $800 million, and it represents more than 2 decades of design, construction, and testing before a single official survey image was ever taken. That is not unusual for a project of this scale. What is unusual is how the team chose to handle the transition from construction to full science operations. Rather than rushing to declare the survey open the moment the hardware was technically functional, the team spent the better part of a year running science validation observations, an extended commissioning phase throughout most of 2025, deliberately testing the instruments, the software pipelines, and the data processing systems under real operating conditions before committing to the official 10-year clock. Every delay in that schedule was a deliberate trade, accuracy and reliability over speed, because a subtle calibration error baked into the system on day one could quietly corrupt years of data before anyone noticed the mistake. Now, let's walk through what has actually happened with real dates and real numbers, because the timeline itself is almost as remarkable as any single discovery. On June 23, 2025, in Washington, D.C., the team behind Rubin Observatory held a public event called First Look, the moment the world got to see genuine images from this telescope for the very first time. One of the first images released was a composite of 2 glowing clouds of gas and dust, the Trifid Nebula and the Lagoon Nebula. Other telescopes had photographed these clouds before, but never like this. That single image was built from 678 separate exposures captured across roughly 7 hours of observing time, and it contained approximately 2 trillion pixels of data, enough detail to zoom in almost endlessly and keep finding stars hiding inside dust that older instruments simply could not resolve. Another image released that same day showed a section of the Virgo cluster, an enormous collection of galaxies, spiral and elliptical shapes glowing quietly behind bright foreground stars belonging to our own Milky Way. Over the full 10 years of the survey, scientists expect Rubin to help catalog roughly 20 billion new galaxies, sitting out there in the darkness right now with no record at all, waiting to be captured. What genuinely stunned scientists, including the people who built the thing, is what happened before the real survey had even officially begun. In roughly 10 hours of early test observations, the telescope had already identified 2,104 previously unrecorded asteroids in our solar system, including 7 near-Earth asteroids that pose no danger to us. 10 hours. Most observatories take years to build a catalog like that. After First Look, the team moved directly into commissioning, fine-tuning every part of the system. And during that stretch, known as the early optimization surveys, something remarkable happened. In about a month and a half, using nothing but this early test data, astronomers working with Rubin discovered more than 11,000 brand new asteroids that had never been recorded before, one of the largest single batches of new asteroid discoveries ever submitted to the International Astronomical Union's Minor Planet Center, the official worldwide body responsible for verifying and cataloging small objects across the solar system. Inside that batch, scientists identified 33 near-Earth objects, none of them dangerous, but tracking near-Earth objects remains one of the most important jobs any observatory can perform, because the more precisely we know their orbits, the better prepared we are for the future. That same early dataset also revealed 380 new trans-Neptunian objects, icy bodies orbiting far beyond Neptune, out in the cold, distant edges of the solar system, where sunlight takes hours just to arrive. 2 of these newly discovered objects have extremely stretched, elongated orbits that carry them nearly 1,000 astronomical units from the Sun at their farthest point, meaning they travel almost 1,000 times farther from the Sun than Earth does. Researchers believe studying orbits like these could eventually help confirm or rule out the long-debated theory of a hidden 9th planet, sometimes nicknamed Planet 9, potentially 5 to 10 times more massive than Earth, possibly warping the paths of distant outer solar system objects. One planetary scientist involved in the project has pointed out that even if Rubin never spots the planet directly, finding more objects with warped orbits would still be an important clue pointing toward its existence. The same early data also let scientists refine the orbits of more than 80,000 already known asteroids, objects that had been tracked before but whose paths were not fully precise, sharpening our entire map of the solar system to a level of accuracy it has never had before. Then, in January 2026, something else turned heads across the astronomy community. Using data gathered during the first look period, scientists published the very first peer-reviewed scientific paper based on observations from the LSST camera itself. What they found was genuinely record-breaking: a rapidly spinning main belt asteroid, larger than 500 meters wide, completing a full rotation in under 2 minutes, the fastest confirmed spin ever recorded for an object of that size. Researchers said an object like this simply could not have been detected without the specific combination of speed and sensitivity built into Rubin's camera. A deputy head of the project noted that finding thousands of new asteroids and learning this much about them in such a short window is only a small preview of what the full 10-year survey is going to uncover. To understand why a spin rate like that is such a big deal, you have to think about basic physics for a second. Most asteroids are not solid rock all the way through. Many of them are loosely bound piles of rubble, held together mostly by their own weak gravity, essentially floating gravel piles drifting through space. Spin one of those objects too fast and centrifugal force should tear it apart, fling the loose material outward until nothing is left holding together. For decades, astronomers have used that basic principle to estimate how solid or how loosely packed different asteroids probably are, based on the fastest rotation rate that still keeps them intact. An object over 500 meters wide, completing a full spin in under 2 minutes, sits right at the edge of what current models say should even be physically possible without the thing flying apart. Which means the single asteroid, hiding in commissioning data nobody expected to produce a scientific paper at all, may end up forcing researchers to revisit assumptions about asteroid structure that have stood largely unchallenged for years. Then came the moment that really opened the floodgates. On February 24th, 2026, Rubin Observatory issued 800,000 alerts to astronomers around the world in a single night. New asteroids appearing, stars suddenly exploding as supernovae, distant supermassive black holes flaring as they feed on surrounding material, variable stars whose brightness rises and falls over time, all cataloged and flagged in one continuous stream. Astronomers called this the true beginning of the alert system, one of the final milestones standing between the observatory and the official start of its 10-year mission. That mission began on June 30th, 2026, following the completed operational review of technical readiness, data quality, and calibration accuracy. From that night forward, Rubin has been scanning the entire southern sky over and over, roughly every 3 days, collecting somewhere close to 10 terabytes of data every single night, with some estimates placing that figure even higher once the survey reaches full operating speed. Across the full 10 years, the observatory is expected to generate roughly half an exabyte of information in total, an amount so enormous that entire teams have spent years building the algorithms needed to sort through it. Scientists have said the data Rubin gathers in just its first year alone will be greater than everything collected by every other optical observatory on Earth combined. Not close to it. Greater than all of them put together. Once the survey reaches full capacity, the system is expected to send out as many as 7 million alerts every single night, each one representing something real changing somewhere in the sky. If a story like this is the kind of space coverage you actually want more of, this channel exists specifically to track projects like Rubin as they unfold. So consider subscribing, because we are going to be covering every major update from this observatory across the next 10 years. And the reveal coming up in a few minutes is exactly why this one is worth sticking around for. Because a flood of alerts that size cannot be handled by a room full of human astronomers checking each one manually. Teams are using artificial intelligence and machine learning systems specifically built to sort through the noise in real time, flagging the events that matter most so researchers around the world can react within minutes, sometimes turning other telescopes toward whatever unusual event Rubin just detected. This is part of what scientists call multi-messenger astronomy, studying the universe through multiple types of signals at once: light, gravitational waves, and cosmic rays working together. When Rubin spots something like a possible collision between two extremely dense objects, or a sudden explosive event somewhere in the sky, it can alert observatories around the globe almost instantly so the event can be studied from every possible angle before it fades away. Supernovae are one of the clearest examples of why that speed matters so much. A supernova happens when a massive star reaches the end of its life and explodes in a burst of light powerful enough to briefly outshine an entire galaxy. And it does not last long, brightening quickly and then fading over days or weeks. If nobody is watching the right patch of sky at the right moment, the event is simply missed. Older telescopes, moving slowly and covering small patches of sky at a time, missed enormous numbers of these explosions for exactly that reason. Rubin solves the problem by never really looking away, revisiting the same regions of sky every 3 days, catching every sudden flare and fading afterglow somewhere inside that repeating cycle, and sending out an alert within minutes of detecting a change that matches the pattern of a dying star. This constant revisiting is also why Rubin is expected to be so useful for something astronomers call failed supernovae, an unusual and still poorly understood event where a massive star appears to simply vanish without the expected explosion, likely collapsing directly into a black hole instead of blowing itself apart. Catching an event like that requires exactly the kind of repeated, reliable imaging Rubin specializes in, comparing what a patch of sky looked like a few nights ago against what it looks like now, and flagging a star that was clearly there before and is simply gone. Very few telescopes in history have ever had the combination of coverage and consistency needed to reliably catch something disappearing rather than something appearing. And it is one of the quieter reasons researchers describe this observatory as fundamentally different from anything that came before it. Phil Marshall, the deputy director of Rubin operations for SLAC, has described the entire journey in fairly plain terms, saying it took 20 years of hard science, engineering, and determination just to reach the point where the team could finally call action and start rolling on what he described as this blockbuster movie of the universe, and that the millions of alerts generated in just the first couple of months of testing already prove the observatory works exactly as intended, a genuine discovery machine, fully assembled and finally switched on. Mike Brown, a planetary scientist at Caltech who has followed this project since his early days in graduate school more than 2 decades ago, has said that working with Rubin's data now feels like something he could only have dreamed about back then, and that if you asked 50 different astronomers what they are most excited to find using this telescope, you would likely get 50 completely different answers because the survey genuinely touches nearly every corner of modern astronomy and astrophysics at the exact same time, every single night. Over the coming decade, scientists expect this survey to reshape what we know about our own solar system in a fundamental way, potentially tripling the total number of known asteroids and increasing the number of identified trans-Neptunian objects by nearly tenfold. To put that first-year projection in context, all other ground and space-based observatories on Earth combined currently discover somewhere around 20,000 new asteroids per year, a number that has taken the entire global astronomy community decades of combined effort to build up. Rubin alone is expected to discover roughly 1 million previously unknown asteroids within its first year of operation, a figure that would represent as many new discoveries as the last 2 centuries of human astronomy managed to produce, condensed into 12 months. That is not an incremental improvement over previous survey telescopes. It is a different category of instrument entirely, and it is part of why researchers who have spent their careers cataloging the solar system describe this moment as a genuine before and after point in the field. And the larger goal, the reason this observatory carries Vera Rubin's name in the first place, reaches even further than asteroids and comets. Dark matter appears to make up roughly 1/4 of everything in the universe, yet nobody has ever seen it directly, only its gravitational fingerprints on galaxies, the very same fingerprints Rubin first noticed decades ago. Dark energy is even stranger, the mysterious force that appears to be causing the expansion of the universe to accelerate rather than slow down the way gravity alone should cause it to behave. By watching billions of galaxies over 10 full years, tracking how they move and how their light shifts, scientists hope this survey can finally help explain what both of those things actually are. Now here is the part almost nobody online has been talking about, and it's the reason I asked you to stay until the end. Back in July of 2025, while the observatory was still deep in its commissioning phase, months before first look was even publicly announced, and nearly a full year before the official 10-year survey began, Rubin was already quietly pointed at patches of sky, running test observations, fine-tuning its systems. On July 1st, 2025, astronomers using a separate network of telescopes called ATLAS announced the discovery of a comet from outside our solar system entirely, an interstellar object now known as 3I, only the 3rd such visitor ever confirmed, after the famous Oumuamua in 2017 and Comet Borisov in 2019. Objects like this do not belong to our sun. They were ejected from other star systems, sometimes billions of years ago, and drift through the galaxy until, purely by chance, their path carries them through our own solar system before they vanish back into interstellar space forever. Here is where it gets strange. After the official discovery was announced through the ATLAS network, Other astronomers went back and started digging through archived data from telescopes that had happened to be scanning nearby patches of sky in the days and weeks before the object was ever formally identified. And buried inside Rubin Observatory's own commissioning data collected purely for internal testing, with no idea an interstellar object was anywhere nearby, they found it. Rubin had already captured 3I, completely by accident, 10 days before anyone on Earth officially knew the object existed. When researchers went back through the full archive more carefully, they found that Rubin had serendipitously photographed the interstellar visitor 9 separate times between June 21st and July 2nd of 2025 alone, then several more times through the rest of that month, some captured on purpose once astronomers knew where to look, some still caught completely by chance. A telescope that was not even finished being calibrated yet, running test sequences nobody expected to matter scientifically, had accidentally created one of the earliest photographic records in existence of only the 3rd interstellar object humanity has ever confirmed, and it sat unnoticed in a data archive for months before anyone realized what they were looking at. Think about what that actually means. This telescope was not even fully operational. It had not begun its real mission. It was still being tested, still being calibrated, still months away from its official first alert, and it still managed to accidentally document a visitor from another star system before the observatory, whose entire job it is to catch objects like that, had even started working. Astronomers involved in the project have said that if a similar visitor appears in Rubin's data once the full 10-year survey is properly underway, the observatory's alert system will catch it directly, automatically, without anyone needing to dig through an archive after the fact months later. Scientists studying interstellar objects now genuinely expect Rubin to detect dozens more of them over the next 10 years, transforming something that used to be a once-in-a-decade discovery into something closer to a routine event.